Today on The Future of Everything, the future of prosthetics and exoskeletons. I have an uncle, Uncle Ron, who lost his leg when he was 7 years old. It was in a driving accident. And in addition to wearing an artificial limb for his entire life, including to this day as he's around 80 years old, Uncle Ron devoted his life to the creation of artificial limbs to help others with the same challenges. I remember him moving for a couple of years to the Fiji Islands where he trained folks in how to create, and this was in the 60s and 70s, create artificial limbs, usually made out of wood. I remember his frequent visits to Vietnam and other areas where war had left landmines, which continued to take their toll on civilians who accidentally set them off and often lost legs. I remember very primitive artificial limbs that he showed me and wore in the 60s and 70s. They had cups for his thigh with padding that were clearly there to try to make it a little bit more comfortable. I remember leather belts for attaching them as securely as possible to his remaining leg. Very crude bending at the knees. I can't even remember if there was bending at the ankles. And there was always an issue of, and for a young boy, this was what I remembered best, the matching shoes. Uncle Ron always had one shoe that he wore on his good leg, on his foot, and then he had the matching shoe that he would strap on to his artificial limb. And for a little kid, that was one of the most fascinating things in the whole kit and caboodle. And it was amazing to see my uncle's facility with walking and activities of daily life. This really did go into the background, and even though he must have had a discomfort, it was never apparent to me, and he was just my uncle. He did tell us about phantom limb pain, where he would have pain in parts of his leg that didn't even exist anymore, and itching. And he said actually the itching was even worse than the pain in many ways. And this all points to the complex relationship between the brain, the limbs, and the nervous system. Now we speed forward, and there's been a development of new materials. We have robotics and software. We have methods for fabrication of prosthetics and even exoskeletons, which we'll hear more about in a minute. And these have advanced markedly. And there are expanded uses. Now we're not just talking about the loss of a limb from trauma, but we now have patients with stroke and the inability to walk and other neurological and muscular diseases. Well, Steve Collins is a professor of mechanical engineering at Stanford. He has pioneered new methods for designing and deploying prosthetics and exoskeletons that simultaneously train the human in how to use these devices, as well as the device to kind of complement the human's capabilities, to harmonize and reach as good a functional capacity as possible. Steve, what do patients today experience when they need a prosthetic device, and how far have we come in terms of providing them useful devices that allow them to just function in their personal and professional lives without having this be the biggest deal?
Sure. Yeah. I mean, hearing about your uncle's story is great, and I think a lot of things are there have been improvements, but there are a lot of features that are really similar today. So people still have this padded, formed, we call it a socket that goes on the residual limb.
Yes.
Yep. And that provides some mechanical connection to the leg. And we now use carbon fiber mostly and better polymers, but it's still trying to do about the same thing. And we now use vacuum suspension to sort of suction cup action to keep it from sliding down instead of those leather straps. I do remember nice.
That some of the woodwork on these legs was spectacularly beautiful. Like when they made a fancy one, it was beautifully varnished and stained, and it really was like a little piece of art, which may have fallen by the wayside, but I do remember that they were spectacular.
Oh, yeah, that was a big component of early prosthetic limbs. One of the biggest suppliers was called Ohio Willow Wood, advertising the kind of wood that they used in forming their limbs. We collaborated with them when I was a graduate student. But many people do, and I have a similar story from when I was a kid. I was much younger, but I met my great uncle, and I was an impetuous 8-year-old or something, and my brothers and I asked him, what happened? How did you lose your leg? And he did this great thing. He said, I'll only answer one question. I'll tell you, but you only answer one question. He said, yeah, okay. It was bitten off. And he left it right like that. And that which was fantastic. And that really stuck with me. Meeting him and learning about his experience.
Was that true?
No, I presume not. I don't know. He only answered one question.
He answered the one question.
But actually, no. I think he lost his limb to diabetes, And also, as it happened, I didn't know this history at the time, but he became really involved in research and was a frequent participant in experiments at the University of Michigan, where I grew up. So anyhow, things have come a long ways in many dimensions, especially with interfacing with the limb. But the basic function of a prosthetic foot, say, is still fairly similar to the device that you described. And many people are prescribed a solid ankle cushioned heel. It could be made of wood or polymer. There's some padding on the heel. And people who are more active will get something that's shaped carbon fiber, so it's more springy. But these are passive devices, so they don't have the ability to do active work like our muscles can do, and they don't have the ability to respond to our behavior and the environment and change how they react to say, help you to power your way upstairs or walk faster or slower or recover from a little disturbance like a bump in the road. And those are the kinds of problems we're trying to address.
And it sounds like, even not knowing very much about it, it seems like there are technologies that, if appropriately used, could help in those areas. And I'm sure that's what you're focusing on.
Yeah, absolutely, we think so, right? And so our group is one of now maybe dozens of research groups across the world that are trying to incorporate these modern robotic technologies into prosthetic limbs that have more of the function that we're accustomed to from our biological limbs. So enable us to walk with less effort and more quickly and with better balance, which are all big problems for people with amputation and stroke. And in fact, we think that because of some of the advantages of robotic devices compared to the biological system, there are a lot of disadvantages, but there are some advantages. We think it's possible to make robotic devices that enable people with disabilities to outperform people who haven't had an injury like that.
Right. So great. So let's do some definitional stuff, because I jumped right into it. But prosthetics, I think most people understand a prosthetic. I was describing the artificial legs, and there are arms. And tell me about exoskeletons, and then we'll go to what the potential use cases are for these, and then we'll talk about where we are in this process. So exoskeletons.
Sure. So you can imagine something from a sci-fi movie, and that's kind of the direction we're headed. Okay. So the most popular vision of this would be the Iron Man suit.
I was going to ask about that, but I didn't want to seem like a fool, so thank you for raising it yourself.
No, but I think they capture this sort of, bold vision of exoskeletons that could not only help recover some performance, but maybe extend your abilities beyond what comes naturally. And I guess this is on a continuum with the kinds of devices people are currently prescribed, which we call orthoses. Mm-hmm. So this is some molded plastic and metal that wraps around your existing limb and tries to help, say, provide more stiffness at the ankle joint to avoid, say, dragging your toe if you have a drop foot or something like that, and or help keep the knee bending the way that we want it to bend during swing, the swing phase of walking, things like that. But they're, again, they're relatively basic technologies, and they can't add power. They can't respond to the environment. And so we're trying to add some of these features that we think are really helpful in human performance.
Got it. So I can think of the exoskeleton as kind of a descendant of the orthotic. Yes. Where we're adding some energy and capabilities.
A powered orthosis is what people called it originally.
I'm sure the applications range from helping people who have had injury, but I'm sure it also could be in the kind of the Iron Man thing, taking people who are kind of perfectly abled under normal observation, but giving them kind of special industrial strength capabilities for industry or entertainment, is that full set of applications kind of in range?
Absolutely.
In your work.
Yes, indeed. So the thing that gets me up in the morning is the idea that we can make devices to help people with disabilities. That's my biggest motivation.
That's the alpha.
Absolutely. But it's really hard. And so a lot of our early work has been with people who don't have a disability, able-bodied folks, mostly college age
healthy volunteers.
Healthy volunteers.
They make the world go.
Exactly. So, and this is where we've had our biggest breakthroughs and progress so far. And we do work with the military, also with the Army, who are interested in preventing soldiers from getting injured when they carry lots of body armor out into the field.
Yes.
And and with
these
some
packs
companies,
can be 50 to 100 pounds, is my understanding.
Yeah, it's ridiculous.
And even though they're young men, this can still take a toll.
Oh, yeah, absolutely. It's a huge problem.
This is The Future of Everything. I'm Russ Altman. I'm speaking with Professor Steve Collins about exoskeletons, orthotics, and prosthetics. Okay, so we have this full range. You've become well-known for this idea of human in the loop as a way to kind of implement a new orthotic and prosthetic technologies. Tell me what that's all about. What's the new idea there? It sounds like humans should have been in the loop all along, but maybe they weren't.
Yeah, well, I guess they were, but we maybe weren't really incorporating that into the design process.
Okay.
So this is a popular topic right now, and last year there were about 5,000 papers and patents in the area of powered prosthetic limbs and exoskeletons. And it's been in the popular imagination for a long time, the media that we've talked about. But to date, there's been only 5 or 10 devices that have demonstrated.
I mean, there was a guy who kicked a football at the World Cup a couple of years ago, and that got a lot of attention.
It did, absolutely. But
almost proving the point that this was not really
right, exactly.
ready.
Right, yes. I think that's a good illustration, right? So, where we think the technology can be is much farther from where it is right now. And so we think that the reason that we've been making relatively slow progress, despite huge investment, big groups, very smart people, is the design approach we've been using, which has been to first use our intuition or observations of some aspects of normal movement or simple models to make a prediction as to what the device should do. And then we spend a few years making something that can embed that functionality. And then we finally get around to testing in a person, and it doesn't work almost all the time.
And does not work. Can you unpack that a little bit for me?
Sure.
Is it it doesn't do as spec'd out,
no,
or the patient hates it, or something in between?
Yes, people often are very excited to try out the new technology, but after a while maybe aren't as thrilled about it. So, but no, it performs the mechanical or robotic function that it's designed to.
Right, because you guys are good and you're engineers. You know how to build something that you've designed.
Absolutely. We're really good at that problem now. We've got fantastic technology, CAD and simulations. But what we're really bad at is predicting how the person is going to respond. And so we think that is the crucial challenge in developing better assistive devices. Is we need to get a faster assessment of how the person responds and involve that response in the design process itself.
Is the hypothesis that it will have to be at an individual level, that different people will have different needs, or do you at least have some hope that if you involve them early, you'll get a somewhat generic solution for multiple people?
I think depending on the population, it could go either way, and we just don't know yet. So we're trying to address both the problem of finding something that works for lots of people and figuring out how to individualize something to, customize it to an individual person's
So
needs.
Can you tell me a story about kind of a story of a human in the loop kind of design effort that kind of worked or looks like it's going to work?
Absolutely. So in our lab, we developed some exoskeletons that help your ankle joint during walking. And for the first 4 or 5 years in the group, we tried lots of different hand-tuned controllers, and we saw modest benefits to the users, improvements in the efficiency of walking. That was our target of about 6%.
So the person has some sort of deficit in their ability of their ankle.
Well, these are, again, we're starting normal with healthy controls.
Okay, so you're just trying to get them to walk more efficiently, so they can either do it longer or faster or whatever.
Yes.
Okay, so that's the goal.
Exactly. With the expectation this could extend.
And you were doing these tuning exercises, which were not panning out so much?
Not going great.
Okay.
No, we saw some small benefits, but much smaller than we thought.
You said 6%. So just help me. Would I recognize a 6% change in my efficiency of walking, or would that be in the noise of like?
Oh no, you would.
I would.
I mean, people make an example I like is the use of your arms in walking. So if you watch people walk, they have this characteristic arm swing, right? That where your right arm moves with your left leg.
Right.
And why do people do that? Well, one reason seems to be to save energy. It actually saves you about 8% of your metabolic
Now,
energy.
there's a good number. So that helps me understand the 6%.
Right. And it sounds like a small number, but yet you watch people walk, they all swing.
And if you try to walk without doing that, which we've all done as a kid, it is very hard.
Yeah. So if you put your hands in your pockets, you can do it. You look cooler, right? But you expend more energy. So you can watch people walking and see how often aesthetics win out over economy. So anyways, these small differences do seem to affect people's behavior, 5-10%.
Okay.
So
good. So I'm sorry. So I derailed you a little bit. You were telling me the story. But so 6% is roughly the benefit you get from swinging your arms, a little bit less. Okay.
Compared to keeping them in your pockets.
Gotcha. Okay.
But we thought we should really be able to do better than this. And so we started developing new techniques for human-in-the-loop optimization, where we would measure the person's energy use while they're using the device. And then we'd feed that information back to this optimizer's algorithm that would then try different behaviors of the device, different ways the device would
tighten
move.
up a bolt or help give a little push at a certain point.
Like when does it push you and how much does it push you? We talk about it in terms of these patterns of force and torque at your joint. And so you walk with this optimizer. Every couple minutes it would change the way the exoskeleton pushed on you. And after about an hour, we found that optimized assistance improved energy economy by 24%.
So huge, 4 times more.
4 times bigger.
And that makes perfect sense, is that you're now you're doing little mini experiments on a minute-to-minute basis. You're getting feedback, and then you have these algorithms, and obviously I'm sure you're using AI and the modern computation to say, okay, we're going to tweak the variables. And that is a personalized kind of prescription, because if you put another person in that same, I'm guessing, tell me if I'm wrong, in that same device, they might benefit from the settings from the previous person, but you have a further ability to tweak. And is that what you're seeing?
That's right. Yeah. We've actually observed in experiments something that makes walking easier for me can make it harder for you. So it depends on the population and the kind of intervention, but you can use this process both to identify things that are generically good for lots of people and ways to customize to an individual person's needs.
And so that's a great example. This is what you mean when you say human in the loop. And this sounds like it's the future for you design a generic solution and then you tune it to which raises a whole bunch of questions that we'll get to in the next segment. This is the future of everything. I'm Russ Altman. More with Dr. Steve Collins about prosthetics, orthotics, exoskeletons next on the SiriusXM Insight 121. Welcome back to the Future of Everything. I'm Russ Altman. I'm speaking with Steve Collins about exoskeletons and prosthetics. So at the end of our last at the previous segment, you made a really interesting comment that even for people who don't have any disability, they have differences in what makes them more energetically efficient in walking. And that's interesting because I've heard also that that somebody's gait, the way that they walk, is almost like a fingerprint, that AI systems can use it to figure out if it's me or not me, because I swing my arms and my legs go out. And I believe that because I look at my kids, and some of my kids walk the way I do, and some of my other kids walk the way my wife does. So what is known about the individual dynamics and physics of walking, and how much variability there is even in the normal population? And does that affect your work?
Oh, sure. Everyone's different. Everybody's body is different, and our nervous systems are different. So as you suggested, I mean, you can tell a person by their kinematics, by the way their body moves, and that affects how you need to assist them. And so we see that if we customize our device to even healthy controls, you get more of a benefit from the device. But the benefit's even bigger in populations where there's more heterogeneity, like people who've had a stroke, it affects everyone really differently. Or amputation, the places you might have pain, how much residual muscle you have, it's different across everyone. And so we expect even bigger benefits of customization in these more diverse populations.
Now, and I don't know if this question is too nerdy, but if you talked about that 24% that you got to with the tuning. If I took that tune system and put it into somebody else, they probably wouldn't get the full 24%. How much of it would they still benefit from the tuning that you did on person A for person B?
Right. So
forgive the nerdiness.
Oh, not at all. No, that's a great question. And so that study I described to you was sort of this breakout experiment for us and very exciting for us. And we've since been following up with lots of additional experiments to probe these kinds of questions. And it looks like if you take the average of the best assistance profiles for 10 people,
right,
and you give it to a new person, they get a lot of the benefit.
Right.
Maybe among healthy controls, maybe 80%.
80%.
Something
it's
like
the
that.
80-20 rule again.
Yeah, exactly. Yeah, totally. And so if you really want to maximize performance, you need to
But
customize.
that 20% is worthwhile. That's
in
worth
some
the
cases,
extra effort,
in
perhaps.
some cases. So I think what we're seeing is that if you want to make a commercial product that's widely available, to keep costs down and to make it easier for a person to use, maybe you want to go for that 80%.
Gotcha.
So you do a lot of upfront development and figure out what's this is still a hard question. What should the generic device look like? But once you have that information, then you can create these customized products and then mass produce them and keep the costs down and actually reach a big market.
Cool, and I want to get to that. I want to end with when are we going to have this on our stores? But before that, tell me, we kind of jumped, this has been great, and we've jumped into a lot of things, but I want to step back. What are the application areas that you see? You said that health drives you in the morning.
Yes.
What are the big areas where you see this can affect, thousands or millions of people and improve their life in terms of like the application areas for this technology?
Sure. So first we have people who really need a device like this, but it's a smaller population, people with disabilities like amputation or stroke. We also have people who really need technology like this because of their occupation, like soldiers, other people who have to, rescue workers, firefighters, carry heavy equipment, go long distances, need to keep going, high injury risk. And then for people that might use them for recreation, like say runners, we have a collaboration with Nike, and you can imagine different ways in which this kind of device could improve people's lives through consumer products, and that could reach a huge audience.
Right. So there's the three big groups, and within the health, I guess because of the aging population, stroke becomes a more and more important application in terms of numbers. What parts of healthcare have the biggest need for this?
Right. Stroke is a huge population. Millions of Americans per year are affected. And amputation, still hundreds of thousands of people have an amputation.
And then I'm sure there are these demyelinating and neuromuscular diseases, multiple sclerosis and Lou Gehrig's disease, where these people could also benefit greatly from these.
Yes, it's tens of millions of Americans who could benefit.
This is The Future of Everything. I'm Russ Altman. I'm speaking with Steve Collins. So great. I wanted to get into those application areas. I know that you've done some work where the human is not in the loop, just robotic walking. How does that interact with the human in the loop part of the lab? Is it that by understanding movement better, it'll inform your work, or is it a separate interest? How does that all fit in?
Yeah. So actually, my walking robot work was very early in my career. I was an undergraduate student. So I was at Cornell University, and I had this fantastic teacher in a dynamics course. His name was Andy Ruina, and he showed this video of this passive dynamic walking robot. So this is a system with no motors, no computers, and walking is just a natural movement of the system.
So it must have been downhill, am I right?
Downhill, yes, exactly.
Because otherwise we're talking about perpetual motion.
Yes.
Okay, so downhill, but then no motors. This is just...
But no motors, right. And so I got involved in this passive dynamic walking research, and then my big project there was to add a little bit of power to allow it to walk on level ground. Very, very simple, primitive stuff, but it resulted in a really energy-efficient walking robot. Similar cost to go a certain distance per unit mass as people.
So can people Google this? Because I'm sure everybody wants to see this. If I did Google it, is it look familiar as a walk? Like, is the solution that the robot found, or that you found, or that your mentor found, does that look humanoid, or is it an entirely different way to go forward?
No, it looks surprisingly natural, like a person walking. At the time, we've argued that it looked more natural than some of the powered robots at the time. Boston Dynamics Alice looks pretty great these days, but this was 15 years ago.
Right.
Anyways, no, the passive movement of the body, really, it is surprising how similar it looks to how people move their body, and it suggested and still suggests that using those passive dynamics is part of what makes a person's gait efficient.
And it's not hard, as somebody who's a geneticist, it's not hard for me to imagine that after a few 100,000 millions of years of evolution, we would have had a solution for walking that is extremely energetically efficient. And it sounds like you've shown that pretty much almost empirically, that it's a very good solution, if not optimal.
Yes, and it's a big area of research in the field, and it looks like people are doing pretty well.
Okay, so I wanted to ask about, so you've gotten us all worked up in a lather about these technologies. Where are we in terms of having them be available for all of those three compelling application areas? How is the industry looking? What are the big challenges? What needs to happen?
That's a great question. So I think that the ways you could see this technology getting out in the world are with the design and prescription and training of these kinds of devices. So just coming up with what kinds of characteristics devices should have, that's a research and development thing. Some of it happens in academia. Maybe some will happen in industry. And at the stage where you actually receive one of these devices, you can imagine kind of the way that you get your glasses prescribed. Yep. There's this big system, and you try different settings and see what works best. And so we imagine we develop these systems we call emulators that are kind of like this VR system for physical devices. So it gives you a feel of interacting with an exoskeleton or a prosthetic limb without having to build it. And then you can, make a few changes in software, and it feels like you're using a different device. And so you can imagine going to a clinic and strapping this on your leg, and then the prosthetist.
Yeah, the eyeglass analogy is a really compelling analogy, because that is a huge machine that turns out into a very simple pair of glasses, and you're having a similar model now.
Exactly. And we think this could result in people getting devices that are much more effective for them.
And actually, this is, again, really technical question, not even technical, but are these going to be huge? These exoskeletons that you see now, are these huge things that I would need a garage to keep it in? I'm sure that that people in your field are thinking about what is the minimal size that we need to generate the forces, generate the motors, and be kind of a compatible with life as a human.
Absolutely.
And how is that going?
That's a really important direction for the field. And looking out 5 years, that's our main focus, is once we know what these devices need to do, distilling that into a cheap and very energy efficient device so that lots of people could get access to it.
So it sounds like, in addition to all of this, you guys are fans of material science and power, batteries, stuff like that, because you're going to need these things to be as miniature as possible and as strong as possible, carbon fiber, whatever. So this would be a critical component of this emerging industry.
Absolutely. We follow those developments very closely. And also new actuation technologies, new ways of converting that energy stored in the battery into mechanical power on your leg.
Because you don't want to take a hit in terms of the energy conversion from electricity to motive force.
Yes. Electric motors are great, but we can do a lot better. They're still pretty heavy and bulky.
Thank you for listening to The Future of Everything. I'm Russ Altman. If you missed any of this episode, listen anytime on demand with the SiriusXM app.